Let us start. It is a considerably big topic, matter like at least two classes, and we have to sum up in one. So let's concentrate on more important points as far as exam is concerned. So hydrogen is the most abundant element that we all know, but is third most abundant element on the Earth's surface after oxygen and silicon. Now, why is it so is important for questions that it is third most abundant on the Earth's surface or the troposphere because of its light weight. है ना? Gravity के कारण it cannot, due to light weight, it cannot be held by gravity on Earth, and it gets uh, evaporated, or I should say, it gets off from the Earth atmosphere. ठीक? Yes, in the form of compounds, it is present on Earth in considerable amount. For example, if you consider ocean, or you consider various compounds like carbohydrate, hydrocarbons, then together they all, and in the form of various compounds, if I consider, it is 15.4% of the Earth crust and ocean. But as elemental hydrogen, yes, it is not present. I'm not doing many questions, but I have incorporated in all the notes so that when I'll share it, you can go through at year end, okay? Because I'll first revise the theory. There are almost 40, 50 questions in the entire set. So when I'll share the notes, you can use them. Now, the next point is the position of hydrogen. As far as the questions or the important point concerning the position of hydrogen in the periodic table is that it has the configuration of 1s1. So it can be like alkali metals NS1, or it could become fully filled outermost orbital by just taking one more electron, right? So if just by taking one more electron, it will become fully filled orbital. Thus, similar to halogens also it can behave, which can just by taking one more electron will become NS2NP6, right? So it can behave both as alkali or halogens. Thus, there is or there has been a little controversy over its position in the periodic table, which of course is still not, I cannot define that it is certainly a 1s group member. It is rather treated as a separate entity. Now, what are the characteristic or the behavior which we can is making it close to alkali metal? So close to alkali metal because it can lose only one electron and become unipositive cation if it forms to if it has to form some compound. ठीक? And its unipositive character or univalency is also making it slightly similar in its other compounds, which I'm not commenting on whether they are ionic or covalent, but just by the mere formula that alkali oxides are Na2O types, M2O, and hydrogen also form H2O. If I compare the the halides of halogen of alkali metal is NaCl, or I can say MCl, here HCl. Similar is the case with sulfide. So these are few things which bring it closer in its property towards alkali groups. Similarly, there are some points of differences also. If it was all good with the similarity, we would have been very confident to place it in alkali, but there are not only just similarities, there are differences. Now, what are the differences? Differences that ionization energy of hydrogen as compared to alkali metals is very, very high, right? Because once it loses that one single electron, it becomes a simple proton, traveling proton, and thus, due to its very small size and resulting just into proton, it does not want to lose that single electron easily. Take. Second is the difference that hydrogen is a non-metal, whereas the alkali metals show all the metallic characteristic properties, which is very unlike to hydrogen. Alkali metals are monatomic in nature. We do not write them as Na2, K2, whereas for hydrogen, we write it as diatomic in nature, H2. So that is again a point of difference from alkali. On the same way, if we compare its similarity and differences with halogens, right? So the high ionization energy of hydrogen, which is 1312 kilojoules per mole, is making it closer or similar to high ionization of fluorine, 1680 kilojoules per mole. So the way halogens do not want to get ionized as cation, same is the story with hydrogen. Halogens exist as diatomic molecule, hydrogen exists as diatomic molecule. Like halogens, halogen forms X minus ions. Similarly, hydrogen, yes, do form hydride ions H minus. We are not commenting on when, where, majority times or not. Those are not our comments. We are just comparing that, yes, there is a possibility. Is that clear? Right? So these were the similarity to halogens. If I compare the point of differences from halogens. So halogens are far more reactive when compared to hydrogen. You remember F2 is very, very reactive, whereas H2 existing around us in atmosphere is certainly not that reactive until unless a suitable condition of temperature pressure is created for it to react, or we bring someone else to initiate the reaction. Okay, so it itself is not that reactive the way halogens usually, fluorine, chlorine, bromine, are reactive. Yes, iodine is not that reactive, but still we can say this is a point of difference. Okay, so overall conclusion that we have to place it separately. It cannot be placed with either alkali or halogen 17th group. Okay. Now, one important information that you have to keep in your mind is size of H plus. That is just, as I said, is a traveling proton, or I should say a traveling nucleus, is just 1.5 into 10 to the minus 3 picometer, which is extremely small. And this is why it always exists in some associated form with either some other atom or as a part of some molecule. Like that, it cannot exist as a free H plus species. Even when we write it in water, we prefer, or we say that it's better to write H3O plus rather than H plus. Yes, we may write for our understanding, but default way we prefer is H3O plus. Correct? Next is different isotopes. In this, there has been numerous questions based on the deuterium, tritium, and some radioactivity of tritium, which are very direct. Okay, simple and direct questions were there. So let's just first go through the theory. So yes, hydrogen exists in three isotopic forms. First is the protium, that is the standard hydrogen in which there is one electron, one proton, but no neutron. Next is the deuterium in which there is one electron, one proton, one neutron. So overall in the nucleus, we have one proton and one neutron. Then there is tritium. Okay, protium is the standard hydrogen or the maximum available isotope that we usually refer. Then comes the deuterium and then comes the tritium. Tritium is, we write as H13 in which one electron, two proton and one electron, one proton and two neutrons are there. Okay, now the percentage presence in nature is certainly least for tritium, then somewhat for deuterium, and very, very large for hydrogen. Okay? Deuterium, yes, is also known as heavy hydrogen, and that is why the D2O is sometimes called heavy. Sometimes in general, it is called heavy water. Now, relative abundance, I would in fact like to insist that it is somewhat like this. This is 99.5 something percentage, which is very, very high. Then comes the deuterium, and this is very, very less tritium. This is important. Tritium is radioactive and emits low energy beta particles. You have to remember this line. Tritium is radioactive, it emits low energy beta particles, and its half-life is 12.33 years. See, this half-life is small. I mean, you may consider 12.33, but still with respect to the starting of universe, if you consider that after so many years it becomes half, so after so many years over the earth existence, the percentage of tritium on earth has become very, very less. Okay, like I would like to say that tritium versus hydrogen in atmosphere ratio is of atoms. Tritium is just one atom to the presence of 10 to the power 18 atoms of hydrogen. So less it has become by now. Deuterium is usually present in a mixed format with hydrogen and deuterium. Like H2 may one atom is of hydrogen and then one is of deuterium. Mostly this is how it is present in the nature. Okay. And it, as I said, its percentage is also very less. It is 0.0156 percentage, which is very small with terrestrial. Terrestrial is something which is present on Earth. So less it is present on Earth. As I said that I have added the question and all so that you can do it. Just an example why I was so emphatic about that statement. This was once asked in mains, which of the following form of hydrogen emits low energy beta particles? And this is not just here. Later stages also you will see questions of this nature where tritium related half-life or the emission of beta particle has been questioned. Okay, so don't worry, they will be part of the question of the notes. But the only thing will be, as Krishna Gupta has asked, where will you share these notes? I'll share it on WhatsApp with the admin and they will most probably forward you. Don't worry. Okay. So coming back to what we were discussing. So as we were discussing their relative abundance, I guess now you can remember this very clearly. 99.985 percentage is hydrogen. 0.0156 is deuterium. And the percentage presence of tritium is only 10 to the minus 15 percentage. Okay. Now, if I compare these three isotopes in their properties, so their chemical properties as their electronic configuration is same, will be same. Okay, their chemical properties will be same. But as the bond dissociation energies of these isotopic hydrogens like H and H, though 435.88 kilojoules per mole, which is high. But still, deuterium is higher, 443.35. Tritium is further higher. So heavier the isotope, more the bond dissociation energy. And more the bond dissociation energy, lesser will be its ease or rate of participation in a reaction. So I can say their chemical properties are similar, but the rate of reaction, the speed with which they will participate will vary. Now I come to the reason assertions. If they say why that particular uh, speed will vary. So you can say higher the bond dissociation energy, less will be the rate of reaction. Okay, so same chemical properties with different kinetics, but they do have different physical properties. Okay? Please notice what is the order. Like relative abundance, we have seen this is the order. Okay? Abundance, hydrogen is maximum. Well and good. Otherwise, rest of the properties, it appears that with increase in mass, relative atomic mass is increasing, melting point is increasing with mass, boiling point is increasing with mass, density is increasing. So it will be easy for you to select the options that only the relative abundance has this type of point, that the hydrogen, the lighter one, is the most abundant, right? Otherwise, with increase in mass, rest all physical properties are increasing.
मैम बॉन्ड लेंथ पूछे तो क्या बताएंगे? बॉन्ड लेंथ
Bond length अगर पूछे तो we practically shouldn't comment. It should be nearly same
ओके मैम,
because
ठीक है.
bond length should be nearly. Oh, it is already given, beta ना.
अरे मतलब अब ड्यूटेरियम का बड़ा बोलेंगे या इक्वल बोलते हैं? मतलब एग्जाम में क्या?
इक्वली बोलेंगे ना, इक्वली बोलेंगे ना, जब हमारे पास यही डाटा है.
ओके मैम.
ये देख
तो ये
इंटरन्यूक्लियर
सब पता था कि डी टू में बॉन्ड लेंथ ज्यादा होती है एच टू से.
नहीं, ये गड़बड़ पड़ा. इंटरन्यूक्लियर डिस्टेंस अपने पास एनसीईआरटी डेटा है. प्लीज डोंट
ठीक है.
रिमेंबर दैट. ओके बच्चे,
ओके.
इट इज इक्वल. मेरे को लगता है तुमने ये तो नहीं पढ़ा कि प्लस आई इफेक्ट ड्यूटेरियम का ज्यादा होता है.
ना मैम,
हाँ,
बॉन्ड लेंथ ही था, मतलब याद है, सही से
बॉन्ड
याद है.
लेंथ ही था, तो वो कुछ गड़बड़ है, उसको भूल
हाँ.
जा.
ओके.
क्योंकि एनसीईआरटी में अपने पास डेटा है कि वी हैव टू कंसिडर इंटरन्यूक्लियर डिस्टेंस टू बी इक्वल. ठीक है मन? इट वाज मन आई गेस ना, आवाज से मुझे मन लग रहा
यस
है.
मैम. यस मैम.
ओके बेटा, ठीक है. So I have again concluded here that if you see the relative abundance, right, that is the only thing which is H greater than D greater than T. Otherwise, it is always heavier mass will be having higher value for that property. Okay. Is that clear? Except for relative abundance, same thing again written, nothing new. ठीक, hydrogen has 3 isotopes. That is again same. Preparation of dihydrogen. Yes, this has been questioned. आया है question. I don't know आप लोगों को assignment अभी हाथ में आया कि नहीं. I don't have any assignment in hand that what has been given to you to solve. But my assumption is we should plan according to the past questions, which are negligible as far as advance is concerned. Nothing as such. So mains is our lot of question source. We should plan around that. Then we should definitely go through each and every question of NCRT, read NCRT twice, and NCRT exemplar. So I have planned my lecture around these three things. Okay, so I have seen exemplar में and NCRT lab उसमें NCRT book में भी इस पर question है laboratory preparation पर. So first question इसमें था कहीं पर कि following में से कौन से में hydrogen बनती है. तो amphoteric metal like zinc, if reacted with HCl or NaOH, in both conditions we get hydrogen. Okay, and this is a very small scale method of preparation. You cannot use it for industrial scale, so it is a lab preparation, but it will give you quite pure hydrogen for the purpose. Okay? Yes, in this whole thing, when you take this acid, acid shouldn't be oxidizing in nature, otherwise the amount of hydrogen produced will be lesser. Commercial. Now, commercial bole to we need large scale preparation where you can produce larger amount of hydrogen. And certainly with the time when hydrogen is to be considered or hydrogen is being researched as a fuel, this is becoming, commercial preparations are becoming important. First is the electrolysis of brine. Brine is just aqueous solution, or rather I should say dilute aqueous solution of NaCl. right? When we do electrolysis of brine, then on cathode, we get hydrogen gas. So it is a byproduct of chloralkali industry. This industry is called chloralkali because during this hydrolysis, you are having chlorine as a byproduct, which is commercially very important, and hydrogen. Okay? So it is called a chloralkali method of, chloralkali industry. In this, we are getting at cathode hydrogen. If we see the arrangement, it is somewhat like this. We have rough sketch, I would say, aqueous solution, okay, of NaCl. Here at cathode, we are having hydrogen. At anode, we are having chlorine. And in this solution with time, NaOH will be present in the solution. This method is for industrial setup of NaOH preparation. ठीक, सोडियम हाइड्रोक्साइड प्रिपरेशन के लिए हमने इंडस्ट्री लगाई एंड बाय प्रोडक्ट्स भी हम सेल कर लेंगे. सो प्रॉफिटेबल इंडस्ट्री आई कैन से. सेकंड मेथड इज
कैथोड यूज होते थे ना.
फिर से बोल
मैम, इसमें तो मरकरी के कैथोड यूज होते थे ना सोडियम को करने के लिए.
वो उसके ये मैंने कहा ना रफ स्केच, वो अलग यहाँ पे बॉटम पे अलग चल रहा होगा.
ओके, मतलब वो ऊपर H2 निकल रही होगी ऊपर.
यस 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 दैट इज मरकरी कैथोड मेथड्स हैं. ये अर्नव की आवाज है.
ओके, यस मैम,
इसकी आवाज है. हाँ,
मतलब
मेरा हाइड्रोजन के साथ साथ आवाज आइडेंटिफाई करने का भी टेस्ट हो रहा है. ठीक कि हाइड्रोजन तो है ही, लेकिन बच्चे पहचान में तो आ रही. तुम दोनों की आवाज तो भी बहुत अच्छे से पहचान में आई कि हाँ ये तो यही है. इलेक्ट्रोलिसिस ऑफ एसिडिफाइड वाटर यूजिंग प्लैटिनम. वो जो अर्नव तूने बोला ना मर्क्यूरी कैथोड वाला, कल एस ब्लॉक है ना, कल उसको डिटेल में करेंगे. ठीक. So acidified water using platinum electrodes. This is in fact a very large scale method because cost effective है. ठीक. तो डायरेक्ट इलेक्ट्रोलिसिस ऑफ वाटर आप करके हाइड्रोजन और ऑक्सीजन को प्रोड्यूस करें. एंड डायरेक्ट मेथड इलेक्ट्रोलिसिस ऑफ एक्वस सोल्यूशन ऑफ बेरियम हाइड्रोक्साइड. हम बेरियम हाइड्रोक्साइड का एक्वस सोल्यूशन लें और उसका हाइड्रोलिसिस करें. यहाँ पर आपको ये याद रखने होंगे कि कहाँ कहाँ पर इसमें प्लैटिनम है एसिडिफाइड वाटर में और इसमें निकल है. ठीक. हमसे लार्ज स्केल प्रिपरेशन जब इलेक्ट्रोलिसिस के पूछे जाता है तो जनरली बेसिक चीजें ही पूछी जाती है कि कैथोड पे बनेगा, क्या बनेगा, कितना बनेगा. ज्यादा ऐसा कोई बहुत टेक्निकल क्वेश्चन आपको नहीं ऐसा परेशान करेगा. हाइड्रोजन obtained is of high purity greater than 99.95% in this last method. Okay? ये बहुत हाई प्योरिटी का हमें हाइड्रोजन बना के देता है. एंड दिस वाज इन फैक्ट आस्क्ड इन 2020 मेंस. एज आई टोल्ड यू ना कि देयर वर क्वेश्चंस, तो वो इसी तरह से आए हैं. यस, देयर इज फोर्थ मेथड व्हिच इज रिएक्शन ऑफ हाइड्रोकार्बन्स विथ स्टीम एट हाई टेम्परेचर. अब आप जब बहुत हाई टेम्परेचर पे हाइड्रोकार्बन CXHY जनरल फॉर्मूला लेकर हम चलें और यहाँ फिर से हमने कैटलिस्ट जो लेना है, ये निकल पर ये काम हो रहा है. एंड व्हाट वी गेट इज अ कार्बन मोनोऑक्साइड एंड हाइड्रोजन मिक्सचर व्हिच इज कॉल्ड वाटर गैस और इज कॉल्ड सिंथेटिक गैस और सिन गैस. सिन गैस इज अ शॉर्टर और एब्रिवेटेड फॉर्म फॉर द वर्ड सिंथेटिक गैस. Okay, this particular synthetic gas is of the name synthetic gas because it is used in preparation of some or different organic compounds. For example, I can take it and form methanol. We'll do after some time. Here I have written like methanol and other hydrocarbons. You can, by action of steam on coke, right? This, just a second, here I had to write syn gas. So by action of steam on coke, up steam or coke is reaction say you have carbon monoxide and hydrogen. This is simply called coal gasification. Okay, this is called coal gasification. Now this CO I want to increase the percentage of hydrogen obtained here. So there is this method. I'll take this CO. I will, to increase the percentage of hydrogen, syngas is reacted with steam. I will again make this carbon monoxide to react with steam. Okay. As a result, when I make it to react with steam, this is my syngas, and I am making it reacting with steam. So what is happening is hydrogen remaining as such. This carbon monoxide is further reacting with H2O and forming CO2, and this H2O, say H2, is converted to hydrogen. Hydrogen mein aaya. So the percentage of hydrogen is increased overall. अगर मैं एक step और ले लेती हूँ तो, है ना? So to increase the percentage of hydrogen, syngas is reacted with steam. Water acts as oxidizing reagent and converts CO to CO2, which could be removed. This CO2 is not a problem. Yes, it is a gas. And we may think how to separate. But CO2 being acidic in nature can be easily removed by using some strong base like NaOH or KOH, in which hydrogen will not be dissolved. Or you can use sodium arsenide solution. This reaction is catalyzed by iron chromate. Okay, this we have to catalyze by iron chromate. And this reaction where we are increasing the percentage, the second step, just the one which is in front of you, this is called water gas shift reaction. Okay, this is called water gas shift reaction. The sixth method of preparation is by hydrolysis of certain metal hydrides. These metal hydrides are those which have hydrogen in its H minus oxidation state, ionic hydrides, I should say. So NaH, you react it with water, you will have hydrogen. CH2 calcium, alkali and alkaline earth metal will form such ionic hydrides which can react with water liberating hydrogen gas. So इनसे हम बना सकते हैं, but we have to be quite careful as ये hydrogen जब release होती है, when this particular reaction takes place, lot of heat is released. Okay, and that heat increases the temperature. As a result, this hydrogen most probably catches fire with oxygen of surrounding. So we have to be very slow and precautious while using this method. Okay? So overall, this industrial hydrogen production that we do in present age is 77 from petrochemical, 77% is from petrochemical products. 18% we take from coal, 4% only we go for electrolysis of aqueous solution, because it is maybe overall cost us a little more. 1% from other sources. Okay. Now here are questions which you can use moving further. Preparation of repeat. Let me just go to where. Yeah. Physical properties of dihydrogen. If I talk of physical property of dihydrogen, you all know that dihydrogen is colorless. कोई हमें दिखाई नहीं देता. It doesn't smell. It doesn't taste. But yes, it is combustible. I just said that it catches fire. Okay, it is combustible, but provided you give a suitable condition. ऐसा नहीं कि मेरे आसपास हाइड्रोजन है और उसने आग पकड़ लेना, ऐसा नहीं. You have to provide it with the suitable conditions. जो activation barrier for that combustion to be crossed. Lighter than air. We have already discussed that it is a lighter gas. It is insoluble in water. This is something that you have already read in somewhere 9th, 10th. Hydrogen gas का bubble का concept 9th, 10th में pop of the hydrogen, है ना? So it was not soluble in hydrogen. This you have already studied in your younger classes. Coming to chemical properties. Now the chemical properties of hydrogen, I can't say that it is extremely reactive as a molecule. Okay, because of its highest bond dissociation energy, considering a single bond of between any two elements, right? HH bond dissociation enthalpy is highest for any single bond. Okay? So it is not easy to break that bond and bring them to the reactions. See, so its bond dissociation energy is quite high. But yes, if we want to dissociate, then you can see that around 2000 Kelvin, you have only 0.081 percentage of dissociation. You increase the temperature to 5000 Kelvin, then it comes to 95.5. Okay, so yes, I can get hydrogen, atomic hydrogen, but it is not that easy to bring it to that level. Okay? But the good thing is, once the reaction is initiated, hydrogen is capable of forming covalent as well as ionic compound. It entirely depends on with which it is forming a bond or with which it is reacting. Coming to reactions with different compounds and all. So first is, we are talking different elements and all. First, we are talking to 17th group halogens. Halogens themselves are very reactive. So the main reason that of this reaction is the reactivity of those halogens. So if I made to react them in this gaseous state, I will have hydrohalic acid HX. Okay. Yes, in this ideal format of reaction, I can write it as FCl-BrI here, X. Okay. But certainly this iodine here, making this reaction feasible, is not that easy. It needs some catalyst to have this reaction. With fluorine, chlorine, bromine, the reaction is taking place on its own. But with iodine, you need to add the catalyst. Okay, fluorine is extremely reactive. It reacts with a boom sound explosion, and even in dark it reacts. But with chlorine and bromine, the reactions relatively slower, controlled. Iodine, we need a catalyst, otherwise it won't react. Okay, coming to reaction with dioxygen. If we make to react it with dioxygen, again, I would insist that the reactions are suitable, conditions are suitable. See, either you need high heat, high temperature, or you need some catalyst. Whichever you can arrange, then you will have the formation of water. Hydrogen and oxygen are combining, and water. If these things were not required, then our surrounding hydrogen oxygen would have reacted and we would have had rainfall. But that is not there. No? So we need the suitable temperature or the catalyst to have this water formation, and this reaction is highly exothermic. Okay? Similarly, like oxygen ke tarike se, similarly other group members of oxygen family, 16th group family, can form H2S, H2SC, H2TE. Okay, oxygen, sulfur, selenium, and tellurium. So they can form that type of compounds, but again, suitable conditions are must. If I talk of nitrogen, every time if you see hydrogen is made to react as a molecule, you will insistingly write either catalyst or high temperature pressure. Okay, suitable conditions. So nitrogen, say be it can react. Nitrogen itself is an inert gas, na? Under suitable condition, and that is what the criteria of Haber process of ammonia formation is. Here we take the iron as a catalyst, and then how we prepare ammonia. Okay? So yes, it can react. Coming to metals, yes, it can react with metals. If you talk of alkali metals, now alkali metals themselves are reactive also, but then also they will not react directly to atmospheric hydrogen. They prefer to react with atmospheric oxygen, right? They catches fire when placed without kerosene on filter paper, but they do not react with hydrogen when placed in open air without kerosene, right? So again, we need to have high temperature to have initiation for this hydrogen to start participating in the reaction. Once it starts, you can have solid salts, ionic salts, I would say, hydrides, which when made to react with water are source of hydrogen. H minus of this salt hydride combined with H2O and hydrogen gas can be released. Okay, but once they are formed, which initially is a relatively difficult reaction. Reaction with organic compounds. In case of organic compounds, if you see unsaturated compounds like alkenes and alkynes, yes, we reduce them or we hydrogenate them. Hydrogenation is addition of hydrogen molecule to these unsaturated compounds in presence of catalyst. Okay, so yes, they react with organic compounds in presence of suitable catalysts like nickel, or you can have palladium or platinum, etc. So reduction is the word that we use. Okay? Commercially, this reaction is used to prepare vanaspati ghee. Okay, artificial ghee, I would say rather. Vanaspati ghee is artificial ghee, and the reaction is catalyzed by nickel in industries. Okay. Now, presently, we have stopped using this type of vanaspati ghee. So you guys might not be aware. These days, we prefer using sapola type of oils. Na? Previously, this was in use. किसी समय 80s में 90s में 80s में I guess it was extremely 70s 80s बहुत ज़्यादा यूज हुआ था तब ये रिएक्शन थी. Yes, in case of organic, one more reaction is there, hydroformylation. Okay, hydroformylation is also something to oxo process. Maybe some of you may remember with this word, some of you may remember with this word, that addition of carbon monoxide and hydrogen in presence of catalyst. Okay, so see, total 3 carbon on that double bond, we have practically added somewhat like, this is not a right, this is just a shorthand for you to remember that in hydroformylation or oxo process, to have the product, you should have a Markovnikov addition of HCO positive and H minus. That will help you to remember the product. Excuse me.
नहीं, ये तो गलत आ जाएगा ना मैम. मतलब H प्लस एंड HCHO माइनस होना चाहिए. मतलब CHO, मतलब CHO माइनस एंड H प्लस.
क्यों बेटा?
तभी मार्कोनिको से होगा. अरे सॉरी, मतलब हाँ ठीक है,
आराम से
सॉरी
आराम से
गलत
तू देख ले, पहले स्क्रीन देख ले फिर बात
अरे
कर.
हाँ, हो गया, मैं
बढ़ू
गलत कर
बढ़ू
दिया,
बढ़ू
समझ गया.
बढ़ू
हाँ
समझ गया
बढ़ो.
ना? हाँ
हाँ
बस. ठीक, तो Markovnikov addition of formyl group and then H minus, shorthand to remember. Again, I'm saying don't remember that this is a mechanism. Okay, I am just suggesting कि इससे आप याद रख सकते हैं that formyl group goes to less sterically hindered site. It's this CHO group. Okay, hydroformylation is an important reaction for organic. हमारे को उतना उसको अलग से याद करने का जरूरत नहीं, but there it will be. And yes, it is further useful because by this method, you are forming alcohols. So it is like entering into a functional group sequence. वहां काम आ जाता है. Sixth point of reactivity is they act as a hydrogen act as a reducing agent. This is the common most which we expect hydrogen to do. Yes, it can act as a reducing agent. Again, I'll say under suitable conditions. It is not that you bring metal oxide and add hydrogen and sit down and say, okay, reaction is taking place. No, there will be either catalyst or high temperature, which will be required. Okay, so under suitable conditions, these reactions will take place. So oxides of less reactive metals like iron, silver, mercury, and all these copper, these can be reduced with hydrogen directly from here to elemental metal state. Okay, others, see, palladium 2 plus iron is reduced. That also we can do. In this process, hydrogen itself is being oxidized to H plus. Right? Now here we are saying that they are reduced to zero oxidation states. But yes, besides this, there is a possibility that the oxidation states of the two oxidation states of the metal, iron, or any species is being changed, like Fe3 plus Fe2 plus type, that is what I want to infer, though here it is not relevant. Okay, टू ऑक्सीडेशन स्टेट इंटरचेंज भी आप देख सकते हैं. अब ब्रिंगिंग इट डाउन टू जीरो ऑक्सीडेशन स्टेट, मेटालिक स्टेट, ये भी हो सकता है. Uses of hydrogen, largest single use of hydrogen is certainly practically आज की डेट में is ammonia, है ना. Then of course we are using it for this vegetable oil and all those reduction organic compound. Then methanol preparation, ठीक, मैन्युफैक्चर ऑफ मिथेनॉल में यूज हो रहा है. यस, होने दो. दिस इज मिथेनॉल प्रिपरेशन एंड आई मस्ट से दिस इज आज, सो प्लीज मार्क इट इंपॉर्टेंट. अरे व्हाटएवर, चलो इस पे लिख नहीं पा रहे, व्हाटएवर रीजन. सो कार्बन मोनोऑक्साइड प्लस ट्वाइस हाइड्रोजन, cobalt catalyst, you have methanol. Okay, in manufacture of metallic hydrides, ठीक है, what is it of importance? We will go to hydrides. Preparation of chemicals like HCl, metallurgical processes में it is used as a reducing agent. ठीक, in atomic atomic torch आप बना लीजिए, which is used for welding, oxyhydrogen, and atomic hydrogen torches which are used for welding or cutting purposes, electric arc की presence में, है ना, how they produce high temperature, right? Hydrogen electric arc and hydrogen is produced. ठीक, these atomic hydrogen is recombined on surface to be welded to generate this high temperature. As a result, metal melts and it joins. So it is used there. And this is the use as a fuel. Rocket fuel में use हो सकता है. This is the most happening branch today, used in fuel cells for generating electrical energy, which is a pollution-free source of energy. This is something which is continuously being researched and developed branch, that how we can use hydrogen as a source of energy, which will be definitely resulting into much less pollution around. But it has its own problems, which we are still working on it. And so it is not a totally clear branch, but yes, we are working on it. This is not in NCERT, but I think just small information would be fine, because in internal exams it appears. Ortho and parahydrogen. Okay, dihydrogen has टू न्यूक्लियर स्पिन आइसोमर्स. न्यूक्लियस के अंदर जो आपके प्रोटॉन्स है उनको स्पिन का बात कर रहे हैं हम. डायहाइड्रोजन हैज टू न्यूक्लियर स्पिन आइसोमर्स, व्हिच वन इज कॉल्ड ऑर्थो हाइड्रोजन, अदर इज कॉल्ड पैरा हाइड्रोजन. See, when two hydrogens combine, then the two electrons, standard of bonding, then the two electrons which form a bond, they have opposite spin, है ना. One goes clockwise, then other वो मतलब ऐसा, तो दूसरा ऐसा, opposite जाएंगे. ठीक, and the opposite so as to cancel their spins and overall making the molecule more stable. However, when we talk of the protons, ठीक, the spin of the protons may be either same or different. Spin of the proton can be same or different. See, electrons opposite. Now protons either, this is a molecule of hydrogen, either both are in the same directions, or you can have proton one like in this direction, one in this direction, anti-parallel nuclear spin that generates the isomerism, that generates the nuclear spin isomerism in these hydrogens. Okay, so if they are having the same direction, parallel spin, then the total spin, one proton is plus half, other is plus half, then ortho hydrogen will have total nuclear spin of 1. In case of parahydrogen, when they are oppositely directed, then the total nuclear spin is 0. Okay, and as you know, ultimately the one with the more nuclear spin will be the less stable one. So ortho hydrogen is less stable than the parahydrogen. Para isomers has low energy and therefore is preferred at low temperatures. Okay, at low temperature. Now, what is the low temperature? Much lower temperature we are talking of. If I talk of room temperature, ordinary dihydrogen surrounding me, then their 75% is still orthohydrogen. So this is not regarded as a low temperature. And 25% is the parahydrogen. Okay, that is what the overall arrangement is. Now here we are starting to talk about the hydrides. We were talking of their reaction, na? So compounds में हम हैं hydrides. Starting for hydrides, this is the general representation I can use. S block. Okay, lithium and sodium, potassium, rubidium, cesium, francium, beryllium, magnesium, calcium, strontium, barium, radium. They form ionic hydrides. Okay, if I talk of D and F block zone, particularly D block, then I have intermediate, or I should say interstitial hydrides. If I go to P block zone, then we have covalent hydrides. उनके और भी नाम हैं, वो हम अभी करते जा रहे हैं. Clear? Let us move. Hydrides. So compound of hydrogen with other elements except inert gases are termed as hydrides. उनको हमने hydride नाम दिया. They are classified as ionic. Ionic are also called saline hydrides. They behave like salts. Okay, so hydrides of S block are termed as ionic because of very high electropositive nature of S block elements. See, still I cannot say they are 100% ionic. All I can say is they have high ionic character. That is a better language rather than using 100% ionic behavior. That I cannot use. Okay, but in S block also, if I talk of beryllium and magnesium hydride, then they are more towards covalent side, and they exist in a polymeric structure. See, so the heavier S block elements are more prone to forming ionic hydrides. See, now properties of these ionic hydrides is they are crystalline in nature. They are non-volatile and non-conducting in solid state, but they conduct electricity in molten state. This line is important. These ionic hydrides conduct electricity in molten state. This line is important. On electrolysis of ionic hydride, hydrogen gas is liberated at anode. I think that is quite logical. It is H minus, anion goes to anode, so hydrogen gas is liberated at anode. By this, we can conclude, in fact, you remember this, that what has been used to prove that hydrogen is in anionic stage in these sol-like hydrides. So you refer the electrolysis of these ionic hydrides, liberate hydrogen at anode, was used as evidence that it has hydride existence. Here, this is used as an evidence. On hydrolysis matlab when water breaks into smaller species like H plus and OH minus. Lysis yani to break. On hydrolysis also, hydrogen gas is evolved. The reaction is violent and thus we can say they are unstable in water. We have already discussed that this can be used as a source of hydrogen, but we need to be careful in lab. Okay? Now, as we have said, higher hydrides. Similar is the story with first group ka lithium hydride being smaller is having higher covalent character. Okay, is unreactive at moderate temperature. Even for reactions with oxygen and chlorine, it won't react. Oxygen chlorine के साथ भी hydride react नहीं करता है. ठीक? What is the use of these ionic hydrides? These hydrides are used for preparation of other. I'm particularly talking now this lithium hydride also in this reaction format. So they are used for as a reducing agent or preparation of some other reducing reagent. Like lithium aluminum hydride is prepared by the reaction of LiH with Al2Cl6. Okay, So hydride acting as a Lewis base, and here ALH3, first hydrogen hydride displaces chlorine, and then it acts as a Lewis base, and ALH3 status ultimately acting as a Lewis acid. We get LiAlH4, which is a very important reducing reagent for our organic chemistry, right? So we get lithium aluminum hydride. If you make it react with B2H6 diborane, sodium borohydride ka bhai, brother of sodium borohydride, LiBH4 is formed. Okay, we get LiBH. If we make it react with trimethyl borate, remember this reaction, then NaBH4 is formed. Please remember this reaction, that this trimethyl borate is used for reaction with NH to form sodium borohydride. They are important reagents, LiLH4, LiBH4, NaBH4. So please remember these reactions. Second type of hydrides are called covalent or molecular hydrides. These are the hydrides of P block. Okay, and these are called molecular hydrides. These are covalent compounds. Still, they are termed as hydrides. Abhi bhi hum bolte hain hydrides, but these are not ionic. These are basically covalent compounds. Okay? Now, these covalent compounds or hydrides are divided into three categories. One, which are electron deficient. Okay, so they ultimately act as a Lewis acid. See, this is the characteristic of 13th group, boron, aluminium, gallium, indium, thallium. In that particular group, B2H6, है ना, उस तरह से electron deficient compounds or hydrides. Electron precise, that is, as many needed are available. Complete electron setting is there. Characteristic of 14th group, CH4. Okay, carbon and its other members. Then tetrahedral structure ke saath they form electron precise hydrides. Then comes the electron rich hydride, 15th, 16th and 17th group. All three form electron rich hydrides, right? Electron rich hydrides I'll share here. Electron rich hydride, and 15, 16 and 17th group form electron rich hydrides. You can see water, H2O, H2TE, H2SE, H2S. See? Then 15th group, ammonia, phosphine, arsine, stibine, bismuthine. Then you go 15th group, 16th group, and now 17th group, HF, HCl, HBr, HI. This is the boiling point order. But these are the hydrides. In all of this, you know that there are presence of lone pair. And now here 16th group, 2 lone pair, 15th group, 1 lone pair, and 17th group, there will be 3 lone pair. So they are called electron rich hydrides. Okay, so 3 covalent molecular hydrides are possible. Properties of covalent hydrides, they are usually volatile because they do not have very strong intermolecular forces. So they are volatile, whereas ionic were solid at room temperature. Due to weak van der Waals forces between the discrete molecules, they are volatile. They have low melting point and boiling point. They do not conduct electricity because there is no free existence of iron. Okay, electron deficient, I have already told, and here you will come across B2H6 structure. Okay, banana bonding, 2 electron distributed on 3 centers, 2 boron, 1 H. Okay, so electron deficient compounds or hydrides from 13th group we'll get. Clear? They act as Lewis acids. Electron precise hydrides. That is, as I said, enough. So CH4, SiH4, GeH4, these are from the carbon family. Electron rich, I have already told. Coming to this point that out of these 3. These 3 matlab nitrogen, oxygen and fluorine, 3 electronegative, strong electronegative elements, when combined with hydrogen forming hydrides, they are capable of intermolecular hydrogen bonding. And as a result, this hydrogen bonding has a strong impact on their boiling point. Okay, this is the order of boiling point of hydrides of these 3 groups. In 16th group and in 17th group, H2O and HF, they have the highest boiling point. That means they have the strongest hydrogen bonding, or I should say the hydrogen bonding impact dominates over the mass. Right? Because boiling point could increase due to 2 reasons. Intermolecular force or heavy mass cannot boil off. Okay. So in case of 16th and 17th, hydrogen bonding is dominating, but in ammonia, or I should say in 15th group, it is not the sole dominating factor. It is somewhere decreased as compared to oxygen and fluorine, and thus you can see the order. Ammonia do not have the highest boiling point. It is the base methane, then stibine, then ammonia, then arsine, and then the phosphine. Clear? Here again you can see that yes, once the hydrogen bond thing is gone, then again it is a case of mass. Tellurium, then selenium, then sulfur, iodine, then Br, then take. Again there are questions. This is from NCERT. Then comes the metallic or non-stoichiometric or interstitial hydrides. This is characteristic of D and F. Now you remember that even in D and F block, 7th, 8th and 9th group. Which group? 7th, 8th and 9th. Now which are these 7th, 8th and 9th group? Let me take you to the here. See, 7th, 8th and 9th. Manganese, iron and cobalt. These 3 do not form interstitial hydrides. In 6th group also, only chromium forms, not the others. Okay, so 7, 8, 9 में कोई नहीं और 6th में only chromium बनाता है hydride. Right. So 7, 8, 9 do not form hydrides. This is termed as hydride gap. इसे बोलते हैं hydride gap. In group 6 only chromium form. Clear? ये याद रखने वाली बात होगी, ये याद रखना है. Now in case of these interstitial hydrides or non-stoichiometric hydrides, small h atom occupies the interstitial sites or voids present in this metallic lattice. This was previously expected that this is how that its original lattice remains same and simply hydrogen occupy these spaces. Okay, so nickel, palladium, cerium, actinium hydrides are like this only, but others में पाया गया कि once they have this hydrogen incorporation, have lattice different from their metal parent. Okay, so this particular that the lattice remains same and hydrogen just enter into the void is not applicable for the entire interstitial hydrides. See, these are non-stoichiometric due to deficiency of H atoms. It is not that exact constant composition law later we can have uniformity of these hydrides. It doesn't hold good for these. See, you can see these are some examples where you can see the hydrogen is not integral. Okay. Properties, they can conduct heat and electricity because metal remains metal. There is no such new bond formed for this metal and hydrogen thing. So they conduct electricity, but of course the lesser extent as compared to the parent metal. See? And the uses, it can accommodate like palladium and platinum can accommodate large volume of hydrogen in their lattice. Thus they are used for storage of hydrogen. See? These are used for storage of hydrogens. Next is water. Water, of course, I think you know all these basic things. So hydrogen bonding, I have already discussed. What you need to know is its ice wala point. है ना? So due to H bonding, water has high boiling point, high freezing point, high heat of vaporization, high heat of fusion as compared to H2S and H2SC. As compared to other liquids, water has high specific heat, thermal conductivity, surface tension, dipolement, and dielectric constant. It is a polar covalent molecule. It is a universal solvent because of its polar nature. Most of the ionic compounds will be soluble in it. And covalent compounds which are capable of forming intermolecular H bond are also soluble in water. जैसे हम carbohydrates हुए, कुछ amino acids हैं, alcohols हैं, these are all soluble in water. ठीक? Water maintains the temperature of body of living beings and of climate due to its high heat of vaporization and high heat capacity. Now here we have to compare physical properties of H2O and D2O. Again, if you check, it is easy to remember that the heavier one, whatever property you consider, every time it is the heavier having higher value except the dielectric constant where H2O is having more than D2O. Those slight difference. But numerically, if I ask, yes, there is. Okay. In case of their isotope, it was just the relative abundance in which the lighter was having higher value. In case of H2O, D2O, it is just the dielectric constant in which the lighter, that is H2O, is having a higher value. Otherwise, simply we can memorize that the heavier one is having higher value. Structure, I think chemical bonding is gone. You all must be aware. Bond angle is 104.5. Bond length is 95.7. As I said, you have to mainly remember about the ice. Water shows hydrogen bonding in liquid as well as in solid state. Density of ice is less than water. As temperature increases, density increases till only 4 degrees centigrade and is maximum at 4. After that, it starts again decreasing as kinetic energy of molecules increases. In ice, water has open cage-like structure due to intermolecular H bonding. Now, स्ट्रक्चर की बात हमें चाहिए ये स्ट्रक्चर ये जो ग्रीन है ये ऑक्सीजन है और ये जो ऑरेंज ऑरेंज है ये हाइड्रोजन है ओके सो ये हाइड्रोजन बॉन्डिंग की वजह से यू कैन सी दैट हाउ इट इज एग्जिस्टिंग एज you can have a just chair like appearance. Okay, several such chair like appearances, and they are then interlinked or interhydrogen bonded is the better word rather than the word linked. Okay, so in eyes it has an open cage, मतलब खुला तो है कोई बंद दरवाजा नहीं है बट फिर भी केज लाइक स्ट्रक्चर है नेटवर्किंग है. When temperature is increased, these hydrogen bonds, which are of course very weak as compared to covalent bonds, start breaking up. And इसलिए density कुछ बढ़ी. This temperature is the reason, this property is the reason for existence of aquatic life in winters. क्यों? क्योंकि जब water temperature कम होने पर freeze होगा, तो ice जो है वो ऊपर की layer पर आ जाएगी. It will come on the upper layer, it will float. है ना? So as the top layer freezes and then it insulates the leftover water. So aquatic life can survive down there. Okay? After 4 degrees, as temperature is increased, molecules start moving away from each other, which results in decrease of density. खुलने लगता है structure. है ना? Each oxygen atom is surrounded tetrahedrally by 4 other oxygen atoms. You can see each oxygen. ठीक? Is surrounded by 4. Yeah, this side, or rather I should relate to this one. See this one. 1, 2, 3, and downside 4, like this. You can see this one. For this, 1, 2, 3, 4 type essay. Okay, so by 4 other oxygen atoms at a distance of 276 picometer. For this one, you can see 1, 2, 3 एंड ये डाउन में जा रहा है 4. ओके, 4 इसके आसपास क्या आ रहे हैं, दूसरी ऑक्सीजन. चेंज इन स्ट्रक्चर ऑफ आइस विथ चेंज इन टेम्परेचर. ये देखो इस तरह का स्ट्रक्चर है. जैसे जैसे हम हीट करें दीज बॉन्ड्स ब्रेक होते हैं. वार्म वाटर है ना, काइनेटिक एनर्जी बढ़ रही है वार्म वाटर में. पहले when these bonds break it becomes cold water, and then when you heat it warm होगा तो again उनका distance भी बढ़ेगा. Variation in density of water with temperature here. Okay, variation structure of ice, this is important. At atmospheric pressure ice has a hexagonal form, but अगर low temperature further करोगे it becomes a cubic form of solid arrangement. ठीक. Chemical properties of water, I think you remember that it is an amphoteric oxide. Autoprotolysis, you remember. Redox reactions, yes. Highly electropositive elements, if are there, like sodium, then they will be oxidized. Hydrogen is released. So what water is doing? Water is acting as an oxidizing reagent and itself is getting reduced. With halogens, see, with halogens, F is becoming F minus. So fluorine is being reduced and oxygen of water is getting oxidized. So here water is acting as a reducing reagent. Here water is acting as a oxidizing reagent. So yes, it can act with reactive elements as oxidizing and reducing. Take these are some more reactions. Also, in photosynthesis, water is oxidized from -2 oxidation state to 0. It is the water which is oxidized. Please remember, in photosynthesis, water is oxidized to give oxygen. Clear? This is a line from NCERT. Disproportionation, we have done this. Hydrolysis. I have already told what is hydrolysis, right? When water breaks into smaller H plus and OH minus. So there is hydrolysis of P4O10, N2O5. See, now it has methods, but due to time shortage, I won't enter like how to remember mechanism and all. N2O3, simply you can add water, at least you do that. And then go for a known formula. To a certain extent, this thing will help. More percentage of oxygen in oxide, if it is so, then acidic nature increases. More the percentage of oxygen in the oxide, in terms of atomic, then it's become more and more acidic. Reaction with metal and oxygen compounds, like metal oxides. So yes, simple hydrolysis, I would say oxide, water forming hydroxides. Solutions are becoming basic. Na2O2 if you take, then there is liberation of H2O2, but this is a peroxide. Oxygen is in -1 oxidation state, right? 6 and so on. A reaction with halides. Not all halides can undergo this type of simple hydrolysis. SiCl4 does, and you can have SiOH4 silicic acid, which ultimately is changing to SiO2 silica, right? CF4 cannot behave like this because it has neither empty orbital in carbon nor in fluorine. Somewhere you need empty orbital for oxygen lone pair to initiate the reaction. Like BCl3 mein boron has the empty orbital. So water can attack on boron. And in SiCl4 silicon had fluorine also, but then silicon is being attacked like that. So BOH3. See? BCl3 hydrolyzed hua, we get BOH3. You can have reaction with nitrite, same way, nothing different. Hydrate formation is different than hydrolysis. Hydrate formation means just addition of water and the water remaining as H2. It is not being split into smaller. then it is called hydrate formation. From aqueous solution, we get hydrates in crystalline form. These could be a following. You can have interstitial water, group 1 and 2, like LiCl dot 2H2 or MgCl dot H, PaCl2 dot 2H2. Coordinate bonds, so you can have water attached. Here, water is present bonded by coordinate bond. See, part of the coordinate here, like this. Or you can have hydrogen bonded. Now, this is important because in CuSO4.5H2, 4 water are coordinate bonded to copper, but one is, okay, one is hydrogen bonded like this. Clear? So one of the water molecule is hydrogen bonded, whereas 4 are coordinate. Clear?
Yes, ma'am.
Moving to next. Hardness of water, I think, I don't know. Have you done in mole? Please reply. Have you done in mole? If you have not done it, please do it. It is very important. There are two types of hardness, right? One is temporary hardness, one is permanent hardness. Overall hardness is due to calcium and magnesium salts. Temporary hardness is due to bicarbonate of these calcium magnesium, and permanent hardness is due to chloride and sulfates of these uh, two metals, calcium and magnesium. Now, how we decide that the water is hard or soft? When we add our soap is sodium stearate, this type. Then what happens in place of the sodium, these metal ions, calcium and magnesium, either when they combine with our stearate anion, C17H35CO minus, then they form a sticky water insoluble scum, or I can say precipitate, which brings this stearate part outside of the water, and thereby it does not have that the leathering or the foam creating thing now. Okay, and the sticky thing sticks to either your wherever you are using this water. If you are using it in boilers, you will have scales of these deposited over there. If you are using for hair wash, you can see your hair will be sticky. If you are using it for your cloth wash, you will feel that hard water won't make them so clean and shiny. Hard water is not suitable for use in laundry, and even it forms scales. Now, two, as I have already told, that chloride and sulfate of magnesium, calcium give permanent hardness, and bicarbonate of magnesium and calcium gives you temporary hardness. Methods for removal. How to remove? Temporary hardness can be simply removed by boiling, but please be careful. Like in very old NCERT, it was, this is correct. Magnesium bicarbonate, when you boil, it doesn't come out as carbonate. Okay, what it gives you is magnesium hydroxide. Okay, yes, the Kp of magnesium hydroxide might be greater than magnesium carbonate, but the solubility of magnesium hydroxide is less than magnesium carbonate. Okay, so boil karte to calcium bicarbonate moves out as a carbonate, but magnesium bicarbonate moves out as a hydroxide, not as magnesium carbonate. Second is the Clark's method, in which we directly add lime. Okay, lime water add karte, direct precipitation of calcium carbonate or magnesium hydroxide, like this. Okay, so that is one way of removing these ions. Permanent hardness is to be removed a little more technically. Here I have to remove chloride, sulfate of magnesium and calcium. So one is the addition of washing soda. That is how the washing soda came into scene. So what is washing soda? You add Na2CO3. Okay. And if you add Na2CO3, these ions of magnesium and calcium, they will move out as carbonate. get them as precipitate and remove, filter. One simple method. Second is Calgon method, in which we use sodium hexametaphosphate. Sodium hexametaphosphate should be rather sodium polymetaphosphate. Okay, it is just one of the case of polymetaphosphate. Okay, fundamentally it is NaPO3 6 times. So what happens? This P6O8, this is somewhat like PO minus O, then P. अब ऐसा 6 times ये करेंगे सारे. This is how it is. है ना, मुझे 6 times ये phosphate करने हैं. Of course the structure 1 2 3 4 5 एक बार और आएगा like this. O minus O, O minus O, O minus, इस तरह के होते हैं. ठीक है. So it is Na6. All these O minus will have sodium. Okay, it is Na6 P6O18. इस तरह का इसका structure होता है. Now what happens? On these negative there is sodium. When we bring it to water, when we dissolve it, Calgon, then it starts ionizing like this. This metal here is either calcium or magnesium. And it forms this type of complex. It becomes part of this. And then due to this salt formation, the calcium and magnesium are maintained in the solution, and then no such stearate ke saath combination and getting out of the medium and forming scum thing happens. Okay, so that was the structure. This is how it reacts, and sodium is removed and calcium and magnesium takes place. And it comes into that place and form soluble. It remains in the solution. With time, when its entire sodium is gone, then we again have to treat that Calgon with NaCl. Okay, that is one method. Another method is by using zeolite, sodium aluminum silicate. We reacted with sodium aluminum silicate, which is NaLSiO4. Now, silicate is a very complicated structure. I cannot just draw like that. All I can say is take this AlSiO4 as Z. NaZ when I made to react with calcium. NaZ I made to react with calcium. Then again, calcium silicate is formed. Calcium aluminum silicate is formed. Okay, like this. Now this calcium aluminum silicate is a solid. You take it out, treat it with NaCl, bring the zeolite back, put it back into the hard water. Okay, now it is not that just one formula is suitable. This is the simplest representation. It could be more. It's zeolite is a big rock. We take that rock and keep. Okay, synthetic resin, ion exchange resin. Now there are two types. Either you can have an ion exchange as a cation exchange or an anion exchange. There are two. But what is this word resin? Resin is basically a big organic molecule. Big organic molecule having SO3H at one end. Okay? Water insoluble, RSO3H. When we make it salt, okay, exchange it to, which is exchanged to RSO3Na, not to RNA, RSO3Na. If I call entire RSO3 as a minus as R, then this is true. Okay, by treating it with NaCl. So we take sodium salt of this resin. Okay, put it in the hard water. Okay, sodium is exchanged with calcium. Okay, sodium goes into the solution. Now, sodium carbonate and sodium chloride, sodium sulfate, they are all water soluble and they do not give any hardness to water. Whereas these calcium and magnesium are brought out of this hard water. Okay, resin is again, take this out, put it back into aqueous NaCl, excess aqueous NaCl. Calcium is again replaced by sodium, magnesium is again replaced by sodium and the resin can be revived and can be reused. The process makes water acidic. Okay, when this, if you take RH directly in place of the salt, if you take RH directly in place of a salt, then H plus is left in the medium. When you take sodium, then Na plus is left in the medium. When you take RH, then H plus, and therefore the solution becomes acidic. In case of anion exchange, the resin is of having this structure, RNH2. Right? So when you add water, when you add it to water, it becomes RNH3 plus OH minus. And now here is exchange of anion. OH